In order to understand the true nature of reality, scientists gave a theory of tiny vibrating quantum strings. In the previous video, we have discussed how string theory was formulated and what makes up the strings. I suggest you to watch that video first, as we are going to continue our discussion from there. In the previous video, we learned that string theory and by extension M theory predicts total 11 dimensions. But how does it even make any sense? How do we explain the existence of other dimensions which will be consistent with our perceived 3D world? As it turns out that there is a way. Let us start with an example. Imagine we lived in a 2D flatland universe. We only perceive the giant x and y directions. Now, what if flatland isn't truly flat? What if the z direction has a tiny width? If someone travels the tiny width of this direction, he will find himself back where he started. Very tiny objects like quantum strings could explore that extra dimension and, most importantly, oscillate in it. But we might have no clue that it exists in the first place. This idea might save the prediction of higher dimensions of string theory. Modern M theory goes ahead a step and proposes an additional large spatial dimension, and our universe of 3D space and 1D time is like flatland on this 5D object called a 5-brane. M theory unites different string theories because it demonstrates some philosophically fascinating dualities between different ways of thinking about the dimensions. Ultimately, it also leads to the ultimate duality, that is, the holographic principle. The exact behavior of strings depends on the shape of their compact dimensions. In fact, the single free parameter in string theory becomes the configuration of the extra dimensions. Finding the right location in this string landscape, we can perfectly describe the universe. The only problem is that there are an estimated 10 to the power of 500 possible choices and almost no way to figure out which one is ours. With that being said, let us discover the reason why physicists are so obsessed with the string theory. Well, its mathematics seems to come together so neatly towards a unified description of all forces and particles. And most importantly, that unification includes gravity. But the fact is, when we start to work out the math of string theory, gravity appears automatically. We don't need to try to add gravity into string theory. In fact, it will be difficult to remove it, and the quantum gravity of string theory is immune to the main difficulty in uniting general relativity with quantum mechanics. It does not give tiny black holes when we try to describe gravity on the smaller scales. But how does string theory dodge the problem of black holes? Let's start with the regular old point particles of the standard model. When a point particle is moving through space and time, it traces a line. On a space-time diagram, time versus one dimension of space is called its world line. In quantum theories of gravity, the gravitational force is communicated by graviton particles. When the graviton acts on another particle, it exerts its effect at an intersection in their world lines over some distance. But in very strong gravitational interactions, that intersection itself becomes more and more point-like. The energy density at that point becomes infinite. More technically, we start to get runaway self-interactions, infinite feedback effects between the graviton and its own field. If we even try to describe very strong gravitational interactions, we get black holes in the math. Now let's switch to string theory, where particles are not points. They are loops or open-ended strands. The graviton in particular is a loop. When strings move on a space-time diagram, they trace out sheets or columns. In fact, we can think of a string not as 1D surface but as a 2D sheet called the world sheet. Now let's look at the interaction of two strings. Now the vertex is no longer point-like. Even the most energetic interactions are smeared out over the string, so we avoid the danger of black holes creating infinities. The world sheets illustrate why quantum gravity is not hopelessly broken in string theory, and that's a huge point in favor of string theory. But these worldsheets will also help us see why string theory predicts gravity in the first place. It turns out that tiny vibrating quantum strings automatically reproduce the theory of general relativity and seem to promise to reproduce all of quantum theory too. We know that vibrating strings are bizarrely well suited to quantization. By quantization, we mean taking a classical large-scale description of something like a ball flying through the air or a vibrating rubber band and turning it into the quantum description. To do this, we basically take the classical equations of motion and follow a standard procedure to turn them into wave equations with various quantum properties added in, like the uncertainty relation between certain variables. This is a tricky process, and it only works if our equations of motions are especially friendly. Schrodinger equation is the easiest example. It quantizes the equations of motion of slow-moving point-like particles. Paul Dirac developed a wave equation for the electron that took into account Einstein's special theory of relativity. It was a mathematical mess until Dirac added some nonsense terms. Those nonsense terms turned out to correspond to antimatter. This is a powerful example of how following mathematics could bring us closer to the truth. Quantizing the motion of strings is done by making use of symmetries. If the physics of a system does not care about how we define particular coordinates or quantities, we say that the parameter is a symmetry of the system or that the system is invariant to transformations in that parameter. Finding symmetries can massively reduce the complexity of the math. A really important type of symmetry in quantum mechanics is gauge symmetry. We can redefine some variable in different ways everywhere in space and still get the same physics. So we expect the phase of the quantum wave function to be a gauge symmetry of any quantum theory. That means we should be able to shift the location of the peaks and valleys in different ways at different points in space without changing the physics. In the original Schrodinger equation, we could not do this. It breaks various laws of physics, but it turns out that we can add a very special corrective term to the Schrodinger equation that fixes these phase differences and it preserves local phase invariance. That term looks like added electromagnetic field to the Schrodinger equation. So in a way, electromagnetism was discovered in its quantum form by studying the symmetries of quantum mechanics. It turns out that exploring a very different symmetry of string theory both makes it possible to quantize the theory and gives us a very different field, the gravitational field. So with our quantized equations of motion in hand, we can predict the quantum oscillations of our string. These are particles and the first mode looks like a graviton, a quantum particle in the aforementioned gravitational field. If we use string theory to write down the gravitational field in what we call the low energy limit, which just means not in places like the center of black hole, then it looks just like the gravitational field in Einstein's theory. But right now, string theory appears to be problematic as it has produced no confirmed prediction. Tuning the string landscape to match our universe is perhaps impossible, yet its promise and its elegance has convinced many that it must be right or at least the way to the right path. Thank you for watching. I hope you liked it. Please like and share this video, and to see such videos in future, do subscribe.